Imagine descending into the depths of the ocean, where sunlight fades and pressure mounts with every meter. Down here, steel giants rise from the seafloor, supporting vital infrastructure that keeps energy flowing and society moving. Yet, beneath their strength lies a vulnerability. A single weld, no wider than your thumb, could decide the fate of the entire structure. This is the realm of underwater structural inspection, where attention to detail and knowledge of welding make the difference between safety and disaster. To truly understand what's at stake, let's first explore the fundamentals of metalwork. There are 4 primary ways metal components are shaped for use: machining, casting, forging, and fabrication. Machining carves away material to create precise parts, while casting involves pouring molten metal into molds to form complex shapes. Forging uses intense pressure to mold metal into robust configurations, and fabrication, the most relevant for offshore construction, brings elements together through joining techniques, primarily welding. Welding itself is a craft with many faces, each suited for different conditions and requirements. Processes are grouped by how they generate heat and protect the weld from contamination. Gas-shielded arc welding, including methods like MIG, metal inert gas, and TIG, tungsten inert gas, uses a protective flow of gas to keep impurities at bay. Flux-shielded arc welding, such as manual metal arc or stick welding, relies on a consumable, flux-coated electrode that shields the weld as it melts. Radiant energy welding uses lasers or electron beams, while unshielded arc welding offers simplicity but limited protection. Some methods, like oxyacetylene welding, use chemical reactions to generate intense heat, and others, like electric resistance and solid-phase welding, join materials without fully melting them. In the challenging offshore environment, flux-shielded arc welding stands out for its reliability and adaptability underwater. With welding as the backbone, understanding its types and associated defects is crucial. Manual metal arc welding is the workhorse offshore, prized for its versatility. However, it's not immune to issues. Undercutting, where the base metal is melted away at the weld's edge, porosity from trapped gases, arc strikes that can weaken the surrounding metal, and lack of fusion, where the weld fails to bond completely. MIG and MAG welding bring semi-automation and speed, but they introduce the risk of incomplete fusion, increased porosity, and spatter. Tiny blobs of molten metal that can compromise the weld's surface. TIG welding, celebrated for its precision and clean results, demands high skill and careful attention to avoid tungsten inclusions, oxide contamination, or burn-through, where excessive heat creates holes. Beyond the weld itself, the way metal pieces join is another layer of complexity. Butt joints, where plates meet edge to edge, provide high strength and are common in critical areas. T-joints form when plates meet at a right angle, like a pipe intersecting a structural leg. Lap joints involve overlapping plates, while corner and cruciform joints connect plates at their edges or in cross-shaped configurations. Each joint type calls for specific welds: butt welds between plate edges for maximum strength, and fillet welds at angles for easier, though sometimes less robust, connections. A welded joint is more than a simple seam. It's a series of zones, each with unique properties. The weld metal, made from molten filler, solidifies at the core. The fusion face marks the boundary where weld meets base metal, while the fusion zone is the region of base metal melted during welding. Next is the heat-affected zone, or HAZ, where the metal's structure has changed due to heat but hasn't melted. This area is especially critical, as rapid cooling can form brittle martensite, increasing the risk of cracking. The parent plate, untouched by heat, retains its original properties. Recognizing defects in these zones is a core responsibility for inspectors. Cracks, the most serious, can occur at the weld's edge, its center, or within the HAZ. Cavities, like porosity and blowholes, result from trapped gases. Inclusions, such as slag or tungsten, become embedded in the weld if not properly managed. Lack of fusion or penetration means the weld has not fully bonded with the base metal, while imperfections in shape, undercuts, overlaps, or irregular bead profiles signal problems with technique or settings. Other issues include arc strikes, spatter, pits, or careless grinding marks. Each defect tells a story, and it's the inspector's job not just to spot them, but to understand their origins and potential impact. Defects are often categorized by their geometry. Planar defects, such as cracks or lack of fusion, are thin and flat, posing a higher risk because they can propagate easily under stress. Volumetric defects, like porosity or slag inclusions, are more rounded and often less critical, but still compromise integrity. Planar defects are especially dangerous in service, while volumetric issues typically arise during fabrication. At critical junctions called nodes, where braces intersect, or at nozzles, where pipes penetrate plates, the complexity increases. Each connection is a potential weak point, demanding vigilance. Accurate defect reporting is paramount, detailing the type, exact location, using clock positions or measurements, dimensions, and a clear description: surface or subsurface, branched or straight, direction and extent. This thoroughness ensures maintenance teams and engineers have the information they need to act decisively. Precision in language is as important as in measurement. Terms like root gap, the space between plates before welding, toe, the weld bead's edge, throat thickness, the minimum cross-section of the weld, HAs, heat affected zone, and cap, the weld's outermost layer, form the vocabulary of effective communication and reporting. Specialized tools bring objectivity and reliability to inspections. Welding Institute gauges measure undercut, reinforcement, and throat thickness, while T-joint gauges are tailored for fillet welds. Mastery of these instruments ensures that every dimension, every angle, and every profile is documented accurately. Continuous learning is the inspector's ally. Study the visual signatures of different defects. Understand the structure of welds and the significance of each zone, especially the HAs. Practice clear, concise reporting, using standardized terminology and precise measurements. With each inspection, sharpen your eye and your judgment. Ultimately, this work is about more than compliance. It's about safeguarding the colossal structures that silently serve above and below the waves. Each weld inspected, each defect reported, is a step toward preserving lives and legacies built on the ocean's floor. The responsibility is immense, but so too is the reward. The next time you descend into the blue, remember, you are not just inspecting metal, you are guarding the backbone of offshore engineering. Embrace the knowledge, wield your tools with confidence, and carry the weight of your mission with pride. For in your hands rests the safety of giants.